Section 28 of The Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in January 2016. The Science History of the Universe, Volume 2, edited by Francis Rolt-Wheeler. Geology. Chapter 14. Crystallography, Part 1. The physicist, as a result of his studies into the structure of different kinds of matter, has concluded that every body is built up of minute particles called molecules, which are much too small to be perceived even by the strongest microscope. When a liquid turns into a solid, because the temperature falls, as when water freezes, or liquid sulfur or molten iron hardens when cooling, the force of cohesion comes into play to bind these molecules together into a rigid mass. So, also, when by slow evaporation from solution, as of salt or alum in water, the dissolving liquid is removed, the substance in solution also passes back into the solid form under the action of this same force of cohesion. Thus, the solid is formed from the liquid by the action of the forces acting between these little particles. Further, if the molecules are all of one kind, as in a given chemical substance, and if there are no hindering causes, these molecules will build themselves up after some regular pattern, and the external result is the geometrical form which is called a crystal. This regular building of the molecules, which may take place from a liquid, happens also, even more perfectly, when a solid is formed direct from a gas. Water vapor in the air, if cooled down sufficiently, is formed into the solid snow, and the little snow crystals that fall silently through the atmosphere are often of wonderful regularity and beauty of form. In nature it often happens that the building process cannot go on freely, and imperfect crystals, or perhaps a mass with only a confused crystalline structure and without distinct external form, is all that is produced. The quartz, feldspar, and mica in the rock called granite usually have formed together in such a way that neither one has had an opportunity to build itself up into perfect crystals, and yet the scientist who understands the optical study of thin sections of a rock in polarized light can prove that each grain, formless though it may be externally, has all the internal molecular structure of the crystal. In the event of a cavity in the granite will be found crystals of quartz and feldspar, perhaps also of mica, as the cavity here means that each has had an opportunity to exercise its tendency to build itself regularly with something of the freedom which a perfect crystal requires. Another familiar example of crystallization is given by the ice covering a pond, which is as truly crystalline in structure as the perfect snow crystal, but here there are no crystals, and it is easy to understand why. The slow dissection of the mass, however, under the melting action of the sun, reveals something of the regularity in the molecular building, and the same thing is proved by an examination in polarized light. Sometimes, in the freezing of a little pool of water, the formation of the slender crystalline ribs of ice may be watched as they shoot out, forming a framework which may soon lose its distinctness as the entire surface is frozen over. Edward S. Dana, in his Minerals and How to Study Them, defines a crystal as the regular solid form which a chemical substance takes when it passes into the solid state from that of either a liquid or a gas, if under such conditions that the molecules are quite free to arrange themselves according to the direction of the attractive forces acting between them. The crystal is, therefore, the outward expression of the structure in the arrangement of those molecules, and its form is for this reason the most important of all the physical character of a given species, and the one which in general most definitely distinguishes it from others. Crystals are therefore, says Professor Dana, the perfect individuals of the mineral kingdom. The mineral quartz has a specific form and structure as much as a dog or an elm, and is as distinct and unvarying as regards those characters, although owing to controlling causes during formation these forms are not always assumed. In whatever part of the world crystals of quartz may be obtained, they are fundamentally identical. It is interesting to note that a small crystal is just as perfect and complete an individual as a similar one of great size. There is among the crystals of a given species no such connection between size, on the one hand, and age and maturity on the other, that belongs to the individuals of a species in the animal and vegetable kingdoms. Some crystals are so minute as to be almost microscopic. Others may be of enormous size, as the gigantic quartz crystals occasionally found in the Alps, or the equally large beryl crystals from New Hampshire. A cave opened a few years ago at Maycomb, New York, contained 15 tons of great cubic crystals of fluorite. Another cave in Wayne County, Utah, contained a great number of enormous crystals of gypsum, some of them 3 feet or more in length. But the very small crystals and the like ones of enormous size are not essentially different, except in this comparatively unimportant respect of magnitude. It is seldom that any mineral crystallizes alone. Usually 2 or 3, under quite different crystalline laws, form together. They do this, comments Ruskin, absolutely without flaw or fault, when they are in fine temper, and observe what this signifies. It signifies that the 2 or more minerals of different natures agree somehow between themselves how much space each will want, agree which of them shall give way to the other at their junction, or in what measure each will accommodate itself to the other's shape. And then each takes its permitted shape and allotted share of space, yielding or being yielded to, as it builds till each crystal has fitted itself perfectly and gracefully to its differently natured neighbor. This seems to imply both concurrence and compromise, regulating all willfulness of design, and, more curious still, the crystals do not always give way to each other. They show exactly the same varieties of temper that human creatures might. Sometimes they yield the required place with perfect grace and courtesy, forming fantastic but exquisitely finished groups, and sometimes they will not yield at all, but fight furiously for their places, losing all shape and honor, and even their own likeness in the contest. All crystals belong to one of 6 classes or systems, which are named as follows: isometric, tetragonal, hexagonal, orthorhombic, monoclinic, and triclinic. The principal forms of the isometric system are the cube, octahedron, dodecahedron, the 2 trisoctahedrons, the tetrahexahedron, and the hexoctahedron. The cube has 6 equal faces, each one of which is a square, and the angle between any 2 faces is a right angle or 90 degrees. Galena and fluorite often occur in cubes. A regular octahedron has 8 like faces, each a triangle with equal sides and 3 equal angles, each 60 degrees. Magnetite is often in octahedrons. The rhombic dodecahedron has 12 equal faces, each of which is a rhomb with plane angles of 60 degrees and 120 degrees, while the angle between 2 adjacent faces is 120 degrees. This is a common form with garnet. A trapezohedron has 24 equal faces, each a 4-sided figure or trapezoid. There may be a large number of different trapezohedrons, all having the same general form, but differing in the angles between the faces. A similar remark may be made about each of the other type forms of this system. A tetrahexahedron is a 24-faced solid, each face an isosceles triangle, and 4 together having the same position as the face of a cube. A hexoctahedron is a 48-faced solid. Each face is a scalene triangle, and 6 faces have the same general position as a face of an octahedron. The isometric system is defined as that system in which the faces are referred to three equal axes at right angles to each other. These axes pass through the centers of the crystals. It will be seen to be true of all these, as it is of all their combinations, that the arrangement of the faces is the same about each one of the 6 cubic faces, or in other words, about the ends of the three axes. There are also several other forms belonging to the isometric system, but which are described as half forms, or forms in which only half of the faces in the corresponding whole form are present. To them the rules of symmetry do not apply, but their faces are also referred to three equal axes at right angles to each other. The most important of these half forms are the tetrahedron and pyritohedron. The tetrahedron is a form with 4 equal triangular faces, each of them an equilateral triangle. The pyritohedron is a 12-sided solid, or dodecahedron, each face of which is a pentagon, but not here as with the pentagonal dodecahedron of geometry, a regular pentagon. In crystallography, the name dodecahedron is usually given only to the rhombic dodecahedron, and this form, the pyritohedron, takes its name from the species pyrite, or iron pyrites, because of common occurrence with it. The chief forms of the tetragonal system are the 2 square prisms and pyramids, and the right-sided prism and double 8-sided pyramid. The square prism has, like the cube, angles of 90 degrees between the faces, but it differs from the cube because the 4 vertical faces are not like the 2 end faces, or basal planes. This is often shown in a crystal by the difference in the smoothness of the 2 kinds of faces, or there may be an easy fracture or cleavage parallel to one set of planes and not to the other. The square pyramid looks somewhat like a regular octahedron, but here the faces are isosceles triangles, not equilateral, and the angle between 2 faces over a horizontal edge differs from that over one of the vertical edges. In fact, either angle is characteristic of a given species and differs from one species to another. The tetragonal system is defined as that in which the planes are referred to 3 axes at right angles, of which the 2 in the horizontal plane are equal, and the third or vertical axis is longer or shorter. In this system there are also some half forms, but only one, the sphenoid, is important. The sphenoid is a 4-faced solid looking like a tetrahedron, but differing from it since the faces are isosceles, not equilateral triangles. The chief forms of the hexagonal system are the 2 6-sided prisms, the 2 double 6-sided pyramids, and the 12-sided prism and double 12-sided pyramid. The angles of the hexagonal prism are exactly 120 degrees, and the terminal face or basal plane is a regular hexagon. The faces of the hexagonal pyramid are isosceles triangles, differing in angle according to whether the pyramid is more obtuse or acute. These angles, and the others that depend upon them, are characteristic for a given species. There is also another hexagonal prism and pyramid diagonal to the others and looking much like them. These 2 sets correspond to the 2 square prisms and pyramids of the tetragonal system. There is also a prism bounded by 12 similar faces, and a double pyramid bounded above and below by 12 triangular faces. This double 12-sided pyramid is often called a berylloid, because common with crystals of beryl. The hexagonal system is defined as that in which the planes are referred to 4 axes, 3 in a horizontal plane, equal and cutting each other at angles of 60 degrees, and the 4th vertical axis either longer or shorter. All hexagonal forms have 3 equal planes of symmetry making angles of 60 degrees with each other, also another set of 3 diagonal to the others, and a 7th plane parallel to the top or base of the crystal. There are several half forms in the hexagonal system, the most important being those of the rhombohedral system. The important forms are the rhombohedron and the scalenohedron. The rhombohedron is a six-sided solid, each face of which is a rhomb. The scalenohedron is a 12-sided solid, looking a little like a double six-sided pyramid, but the faces are scalene triangles and the edge is zigzag, up and down, like that of a rhombohedron, instead of horizontal as in the pyramid. The number of species crystallizing in the rhombohedral division of the hexagonal system is very large, and some of them, as for example calcite, are very highly complex. The characteristic forms of the orthorhombic system are the rhombic prism and pyramid. There are also other forms called domes. In a rhombic prism, the terminal face, formed by the basal plane, is a rhomb, not a square as in the square prism, which it somewhat resembles. There may be a great many rhombic prisms on the crystals of the same species, differing in the angles of their two edges. The rhombic pyramid in cross-section, like the prism, is a rhomb, and its edges belong in three sets, with different angles for each. These angles are characteristic for the crystals of a given species. The forms called domes derive their name from the Latin for house, domus, because when they meet above they make a horizontal edge like a hip roof. These domes are often and very conveniently called horizontal prisms. In the orthorhombic system, the planes are referred to three unequal axes at right angles to each other. The grouping of faces about the extremities of each of the axes differs from that about the others, but there are three planes of symmetry which are all unlike. In an oblique rhombic prism, the end plane is rhombic in form, but it is oblique to the faces of the prism, instead of being at right angles as described in the orthorhombic system. This oblique prism, and a variety of other forms of the same group, belong to the monoclinic system, in which the planes are referred to three unequal axes, two of the angles between which are right angles, while the third, in front, is obtuse. Monoclinic forms are very complex, and for technical description it is necessary to consult a larger work which has space to deal with the geometrical names of the prisms. They have only one plane of symmetry, and appear as prisms, pyramids, and domes. Finally, there is one other group of forms which belong to the triclinic. In this system the planes are referred to three unequal axes, all oblique to each other. Here all the intersections are oblique, and the like faces are in pairs only on opposite sides of a crystal. There is no plane of symmetry at all. Triclinic forms are even more complex than those of the preceding systems. End of section 28.